9.2 Parametric Equations and Arc Length. We know that parametric equations can be used to describe the path of an object moving in a plane. This leads to asking the question, how far has the object traveled? A particle moving along a curve in the plane with parametric equations x equals f of t and y equals g of t, where t is time, has speed given by the absolute value of velocity, which is equal to the square root of dx dt squared plus dy dt squared, or the square root of x prime of t squared plus y prime of t squared. We can find the distance traveled by the object moving along the curve between 2 points t equals a and t equals b by integrating its speed such that the distance traveled is the integral from a to b v of t dt. And assuming the object never stops or reverses its direction as it moves along the curve between A and B, the distance traveled is the length of the curve, okay? So basically this is like your average rate of change. This is like your instantaneous rate of change. This is your speed. It is the absolute value of velocity. Remember, velocity has a sign that tells you the direction that it is going, where speed is just the absolute value of that, always positive. And this is distance traveled under these conditions right here, or it would also be known as the length along the curve from A to B, okay? So now, example number 1, an equation of the form y equals f of x, where x is between A and B, has an arc length L of such a curve is given by the definite integral below. Use the formula below to find the arc length from x equals 0 to x equals 3. So this is the arc length of this function for any value a to b. Okay, they want you to find the arc length from 0 to 3. And so before I find or finish this, I need to take and find out, oh my, this keeps, and I don't know how to delete it either. I know that's stupid, but I guess I can just erase it. There we go. I need to find my y prime. So you have your 1/3 that is basically out in front. You're going to bring your 3/2 down times 4x to the 3/2 minus 2/2, and then times the derivative of 4x. So that is your derivative. And now we just have to divide by 3, divide by 3, divide by 2, divide by 2. And so this is going to end up being 2 times the square root of 4x. So this is going to be 2 times the square root of 4x squared dx. And so now we just need to start simplifying. So the integral from 0 to 3, square root of 1 plus 4 times 4x dx, integral from 0 to 3, square root of 1 plus 16x dx. And then we're going to make our u, because now to solve this integral, you're thinking, okay, well, if that whole thing was my u, what would my du be? My du would be 16 dx, and then you could put du divided by 16 in for your dx. So this is going to be L equals the integral. I'm not going to put my my 0 to 3 in because I am substituting with u. So I would like to find what my u of 0 is, and it looks like my u of 0 is 1. And I would also like to find out what my u of 3 is, and it looks like my u of 3 is 49. So this becomes 1/16 times the integral from 1 to 49 of u to the 1/2 dx. And I'm going to move this up to here, put a line there. So we've got length along the curve is equal to 1/16 times. Now this is going to be u to the 1/2 plus 2/2, And then divided by 1/2 plus 2/2 is multiplication by 2/3. And this is going to be from 1 to 49, and I'm not going to put my equivalency back in. I'm going to leave it u. Divide by 2, I get 1. Divide by 2, I get 8. So this becomes 1/24th, and this will be the square root of 49 to the 3rd power minus 1/24 times the square root of 1 to the 3rd power. So 7 to the 3rd gives me 343 divided by 24 minus 1 divided by 24, which leaves me 342 divided by 24, which they are both divisible by 6. So that will simplify to the arc length as 57/4. And so again, this is the arc length from 0 to 3 along this curve. Okay? And so basically, you're basically just using your formula. Okay? They told you that this is your arc length here. But now we're going to say the arc length in parametric form. If a smooth curve C is given parametrically such that C does not intersect itself on the interval between A and B, except possibly at the endpoints, then the arc length of C over the interval is, and we usually call arc length S. S is equal to the integral from A to B v of t dt, which is the integral from A to B square root of dx dt squared plus dy dt squared dt. And then that is the same thing as the integral from A to B of the square root of f prime of t squared plus g prime of t squared, when f of t is a function of x in terms of t, and g of t is a function of y in terms of t. So now, we've got the official definition here. Example number 2, Randy the Roach is moving in the xy plane. At time t, his position is given by the parametric equations x of t comma y of t, where dx dt is 3t and dy dt is t squared. Find the distance Randy traveled from t equals 0 to t equals square root of 15. So we're going to use that formula, We're going to say that the arc length S is equivalent to the length along the curve from 0 to the square root of 15. Square root of my dx dt is 3t, so 3t squared, plus my dy dt is t squared squared dt. So this becomes the integral from 0 to the square root of 15, square root of 9t squared plus t to the 4th dt. So integral from 0 to the square root of 15, I'm going to factor t squared out, and then I'm going to set this up as two separate square roots. Square root and square cancel. And so from that point, since I know that t squared has a derivative that is going to maybe cancel the t on the outside here, I'm going to make my u 9 plus t squared. And then my du is just 2t dt. So du divided by 2t is my dt. So now I'm going to leave this as t on the outside. I'm going to make this the square root of u, and I'm going to put in my du over 2t, and my t's cancel. So this is going to be 1/2 integral u to the 1/2 du. And now that we have u's, let's go ahead and find our u of 0. That's going to be 9. And let's find our u of the square root of 15, which is going to be 9 plus the square root of 15 squared. So 9 plus 15 is 24. So that would be from 9 to 24. So I've got 1/2, and then I have u to the 1/2 plus 2/2, so that's to the 3/2, and then divide by 3/2 is multiplication by 2/3. And the 2's cancel. So now we end up with 1/3. This is the square root of 24 to the 3rd power minus 1/3 square root of 9 to the 3rd power. And remember that the square root of 24, it does have a 4 in it, so that's going to be 2 root 6. So this would be 1/3 times 2 root 6 cubed minus 1/3 times 3 cubed. So 1/3 times 2 cubed is 8. And the square root of 6 times the square root of 6 is 6. So this is going to be times 6 root, oops, I almost put root 3, 6 root 6. Minus, divide by 3, I get 1, divide by 3, I get 1, or I get 2. This is going to be minus 9. Divide by 3, I get 1, divide by 3, I get 2. This is going to be 16 root 6 minus 9. And if I put that in my calculator to find out the approximation, it would be approximately equal to 30.192. But 16 root 6 minus 9 is your exact, okay? All right, example number 3. Find the length of one arch of the cycloid with parametric equations. X equals theta minus sine theta, y equals 1 minus cosine theta. I did end up making like a chart here for each one of my thetas because it said along one arch. Well, if you put this in your calculator in parametric form, you're going to see that one arch ends up being from 0 to 2 pi. Okay, because it's going to complete a cycle. And I can show you that if you need me to. I'll just have to bring up that calculator. So if my theta was 0, for x I would have 0 minus the sine of 0, which is 0. For y I would have 1 minus the sine of 0, which 1 minus 1 is 0. If my theta were to be pi over 2, I would, for my x, it would be pi over 2 minus the sine of pi over 2. So that's pi over 2 minus 1, because the sine of pi over 2 is 1. And if you gave me an approximation, well, I'm not even going to do an approximation for right now, but I can come back to that. And then my y is going to be 1 minus the cosine of pi over 2, which is 0. So 1 minus 0 is just 1. The next one I'm going to look at is at pi. And if I put it in for x, it's going to be pi minus sine pi. Well, sine of pi is 0, so this is just going to be pi. And my y is 1 minus the cosine of pi. That's 1 minus a minus 1, so that's 1 plus 1, which is 2. The next one I'm going to do is 3 pi over 2. So x is equal to 3 pi over 2 minus the sine of 3 pi over 2. The sine of 3 pi over 2 is negative 1. So that's 3 pi over 2 minus a minus 1 is going to be 3 pi over 2 plus 1. And then y equals 1 minus the cosine of 3 pi over 2. Well, the cosine of 3 pi over 2 is 0, so that's 1 minus 0, which is 1. And then the last one is 2 pi. 2 pi minus the sine of 2 pi. The sine of 2 pi is 0, so 2 pi minus 0 is 2 pi. And then y equals 1 minus the cosine of 2 pi. Well, the cosine of 2 pi is 1, so 1 minus 1, that is 0. So if we just do a little sketch just to make sure we know what's happening here, we do have 0, 0. Okay, so let's say that's pi over 2. Let's say that's pi, 3 pi over 2, and 2 pi. And so our highest one is going to be 2. So at pi, it's at 2. This one is going to be about here. This one's going to be about here, and this is 0. So basically, there's your one arch of that function. And that's why it works. So now let's go ahead and use our formula. From 0 to 2 pi is our integral. And this is going to be the square root of dx d theta squared plus dy d theta squared. So 0 to 2 pi, square root of. Now, let's go ahead and figure out what our dx d theta and our dy d theta are. Let's go ahead and put those right here. Our dx d theta is going to be 1 minus cosine theta. And our dy d theta is going to be 0 minus sine, so that's plus sine. Okay, so this is going to be 1 minus cosine theta squared plus sine theta squared. So 0 to 2 pi, square root of. This is going to be 1 minus 2 cosine theta plus cosine theta squared plus sine squared theta. I forgot my d theta. Sorry, guys. D theta. There's my d theta. And notice that cosine squared theta plus sine squared theta is 1. That's your Pythagorean identity. Okay, so look at that as the Pythagorean identity, and it is equal to 1. So this becomes the integral from 0 to 2 pi, square root of 1 minus 2 cosine theta plus 1 d theta. So I've got a positive 1 and a positive 1. Integral 0 to 2 pi, square root of 2 minus 2 cosine theta d theta. And then from there, since this is, it's hard to get this one to change to anything, but since it is a calculator one, let's go ahead at this point and put it in our calculator and see what we get. Integral from 0 to 2 pi, square root of 2 minus 2 cosine theta d theta. And you should get 8 when you put it in your calculator. Okay, example number 4. For t greater than or equal to 0, a particle is moving along a curve so that its position at time t is x of t comma y of t, where x of t is shown in the graph at the right. For the particle y of t equals x of t squared. Find the speed of the particle at time t equals 1. So anytime I'm looking for speed, I always remind myself that it is the absolute value of velocity. And we did define it to be the square root of our dx dt squared plus our dy dt squared. And so this becomes the square root of, now our dx dt, if we look at, because we're actually finding our speed at 1. So this should be, now that we're going to start putting our values in, the velocity at 1, but taking the square root of it. So this dx dt is going to be the derivative of x at 1. So if I look over here, and I knew this was x, at 1, my slope of my tangent line is just the slope of this line. So I could go from here, to here or whatever, and do rise over run. So I'm rising 5, I'm running 2. So my slope's going to be 5/2. And our dy dt, our y of t is x of t squared. So our y prime of t is going to be the derivative of t squared, which is 2t, times x prime of t squared. And then I need to find my y prime of 1. So that's 2 times 1 times x, and then of 1 squared. X prime, sorry, of 1 squared. I mean, yeah, x prime of 1 squared. So 2 times x prime at 1. And we said that the derivative at 1 was 5/2. And so this gives us 5. So for this one, I am 5 squared. Oops. I don't have an integral. And so this is going to be the square root of 25/4 plus 25. So if I wanted to change these into fourths, I would multiply this by 4/4, and this would give me 100/4. So this is the square root of 125/4. And so to simplify that square root of 125 here, I know that it is the same thing as the square root of 25 times the square root of 5 over 2. So 5 root 5 over 2 is your exact answer. And if you wanted to give an equivalency in your calculator, you can. But I'm just going to leave it exact. All right. Example 5. At time t, the position of a particle moving in the xy plane is given by the parametric functions x of t, y of t, where dx dt is 2f prime of 2t, and y of t is the square root of 3 times f of 2t. The function f of t is continuous and differentiable with selected values shown in the table below. Find the distance traveled by the particle from t equals 1 to t equals 5. So one thing I did do is I just stated what my, because I knew it was going to be in my formula, what my dx dt was. So it was 2 times f prime of 2t. And my dy dt, we need to calculate. I'm going to take the derivative of 2t and multiply it by the square root of 3. So this is going to be 2 times the square root of 3 times f prime of 2t. Okay, so that is my dx dt and my dy dt. So now I'm looking for distance traveled. And so it is going to be the integral from 1 to 5, absolute value, v of t dt. And this will be your integral from 1 to 5, absolute value, or I'm sorry, not absolute value, square root of dx dt plus squared plus dy dt squared. Okay, and now integral from 1 to 5, square root of, my 2 squared is 4, and then times my f prime of 2t squared. And then when I square my 2, I get 4. When I square my square root of 3, I get 3. Times f prime of 2t squared. And then these are both f prime of 2t squared. So I've got 4 and 12. So I've actually got the square root of 16 times f prime of 2t squared. And I can split those up into 2 separate square roots. I can say the square root of 16 times the square root of f prime of 2t, that whole thing squared, which they are going to cancel. And the square root of 16 is 4. So integral from 1 to 5, 4 times f prime of 2t. dt, sorry. Okay, so let's bring our 4 out in front. Integral from 1 to 5 f prime of 2t dt. And so this is going to be 4 times f of 2t divided by 2, because I'm taking the integral, remember, so I'm going to have to divide by the derivative of 2t, and then from 1 to 5, and divide by 2, divide by 2. This becomes 2 f of 2t from 1 to 5. So that's 2 times f of 2 times 5, which is 10, minus 2 times f of 2 times 1, which is 2. So f of 10 is 9, so 2 times 9 minus 2 times f of 3 is, f of 2, excuse me, is negative 3. My notes have a negative, but it's supposed to be a positive, I guess, because my paper that I'm looking at is a positive. I don't know. So if this is a positive on your paper, then your answer is going to be 18 minus 6. But if for some reason that is a negative like mine was, it would be 18 plus 6. So, you know, it's just whatever that is. Whatever f of 2 is, you need to put it in right here and solve this, okay? Because it looks like the paper that I did the work on has positive 3 there, and the one that I have right now that I'm working with you had negative 3, but I'm going to cross that negative 3 out and put a positive 3. It looks like all the other values are exactly the same. Yep, because I just checked all of them. The only one that wasn't was, of course, this one that we needed. So, but my answer is 12 if you have positive 3 there. Oops. Okay. And example number 6. So for example number 6, it says at time t, the position of a particle moving in the xy plane is given by the parametric functions x of t comma y of t, where dx dt is t squared plus sine of of t squared, and the graph of y consisting of 4 line segments is shown at the right. When t equals 0, the particle is at the point 4, 7. So find the slope of the line tangent to the path of the particle at t equals 3. Well, the slope of the tangent line is always dy dx. I told you that on the last slide, I think. And so that is found by taking your dy dt divided by your dx dt. If they want it at t equals 3, then this will be at t equals 3. And so if I wanted my dy dt at t equals 3, I would go up here and I would be looking for the slope here. And this slope would just be rise over run from this point to this point, 1, 2, 3, 4 over negative 2. So that's going to be a negative 2. And then dx dt at 3 is going to be 3 squared plus the sine of 3 squared. Sorry. So negative 2 over 9 plus the sine of 9. And if we put that in our calculator, we should get approximately negative 0.212. So that would be the slope of the line tangent to the path of the particle at t equals 3. Find the speed of the particle at t equals 3. Well, that would be absolute value of v of 3, which we define to be the square root of, this would be our dx dt at t equals 3 squared plus our dy dt at t equals 3 squared. So our dx dt at t equals 3, we said was 9 plus the sine of 9. And then our dy dt t equals 3 was negative 2. So that squared plus that squared. Square root of. I'm just going to leave this because this is a calculator problem. I'm going to leave this as 9 plus sine 9 squared and then plus 4 underneath the root. So if I put this in my calculator, I should get 9.622. And then for part C, find the position of the particle at t equals 3. Well, it said that when t equals 0, the particle is at the point 4, 7. Actually, again, I just found another mistake. I don't know if you guys have 7 or 0. I think it's 0 now. I don't know which one is right, but I think this says 40. It says it on the one that I printed out that I think is exactly the same as yours. So let's use the point 4, 0. So we are going to start at the point 4, 0. Okay, so our x of 3 is going to be our x of 0 plus the integral from 0 to 3 of x prime of t dt. So our x of 0 is 4 plus, and then I just put this, the derivative, the integral from 0 to 3 of that t squared plus the sine of t squared dt. And I put that in my calculator, and it gave me like 9.773562. And so I said this was roughly 13.774. And this was my x of 3. My y of 3 is going to be my y of 0 plus my y of 3. And so my y of 0 was 0. My y of 3, if I go up to my function or my graph up here, I can see that my y of 3 is 4. So this is 4. So at time t equals 3, the particle is at 13.774, 4. And then part D, find the equation of the line tangent to the path of the particle at t equals 3. So I'm looking for the equation of the line tangent to at t equals 3. Well, we found up here that the slope was negative 0.212. So y is equal to negative 0.212 times x minus 3. I'm sorry, not x minus 3. I got to do x minus my x1 at time 3. Sorry, x minus 13.774, and then the y is 4. So I had to include this point and this slope, and that gave me the equation of my tangent line.